Hi, I am Sanjay Patel. Today, in this video, we are going to derive the relationship between beta and gamma function. This is one of the most important result about beta and gamma function. So let us write as a theorem. Prove that beta of m comma n is equal to gamma m gamma n upon gamma of m plus n. Okay, let us prove. We will begin with the definition of gamma function, and I will write the values of this numerator gamma m and gamma n. So we know that gamma of m we can write as 2 times integral 0 to infinity x raised to 2m minus 1 into e raised to minus x square dx. We have derived this result in the properties of gamma function. The same way we can write the value of gamma n also. And this time I want to use a new variable because a variable is not important here. So let me use a new variable y because I want to convert this multiplication into a double integral. So this I can write as y raised to 2n minus 1 into e raised to minus y square dy. So I'm using the variable y instead of x. Okay, then multiplying these two, we get, so therefore gamma m into gamma n is equal to, say, this 2 into means multiplication of these two gives you, let me write, integral 0 to infinity x raised to 2m minus 1 e raised to minus x square dx into 2 times integral 0 to infinity y raised to 2n minus 1 e raised to minus y square dy. And here you note that both of these variables are independent. No function contains the variable of the other function, and also limits of integration are constants. So this I can write as 2 into 2 4 times double integral 0 to infinity and this thing x raised to 2m minus 1 into y raised to 2n minus 1 into e raised to minus x square minus y square into dx dy. Okay, let us call this as star, and observe that this double integral is to be evaluated over the region where x varies from 0 to infinity and y varies from 0 to infinity. So the above double integral is evaluated or is defined on the region R given by this, all those points x and y such that x is greater than or equal to 0 and y is greater than or equal to 0. So x varies from 0 to infinity and y varies from 0 to infinity. So the region of integration is nothing but, say, the first quadrant. So let me show you so that you will get some idea. So it is the first quadrant. So this is my region of integration. This is say x-axis, this is y-axis, and this is origin. So this whole thing is our region of integration. This whole part is region of integration, say R. Okay. And what I want to do is I want to change these variables, these double integrals. I want to transform this double integral into polar coordinates. So transforming the double integral in star into polar coordinates by taking, you know what is the relationship between the Cartesian and the polar coordinates. So I am taking x is equal to r cos theta and y is equal to r sin theta. Okay, and also you know if this is the relationship, then x square plus y square is equal to r square. And also when you change the variables from Cartesian to polar, the differential in the double integral dx into dy is replaced by r into dr d theta. So we take the same, this origin as pole and this as initial line in the polar coordinate system. So in this case, when x varies from 0 to infinity, here x varies from 0 to infinity and y also varies from 0 to infinity. Okay. So how does that r and theta changes? The theta changes from this point to this point. So it is obvious that theta changes from 0 to pi by 2. Let me use some other color so that it is visible. So this is theta is equal to 0 and theta is equal to pi by 2 line, pi by 2. Okay, so theta varies from 0 to pi by 2 and that r, it changes from 0, that is origin, up to infinity. Okay, so r varies from 0 to infinity. So let me write and mention that here as x and y varies from 0 to infinity, we have r varies from say 0 to infinity and theta in the polar system, theta varies from 0 to what? Theta varies from 0 to pi by 2. That I have already explained. Okay. So keeping in mind all this, now I can transform this double integral, that is gamma m into gamma n here, and write this star as follows. So therefore from star, from the result star, we get gamma m into gamma n, which was, let me rewrite that so that you can understand, integral 0 to, say it was infinity 4 times, integral 0 to infinity, then x raised to 2m minus 1, y raised to 2n minus 1, e raised to minus x square minus y square, and dx dy. This is replaced by 4 times r is equal to 0 to infinity, theta varies from 0 to pi by 2. What is x? X is r cos theta. So I will write here r cos theta raised to 2m minus 1. Y is r sin theta this raised to 2n minus 1 into e raised to minus r square, because x square plus y square is r square, and dx dy is replaced by r into dr d theta, as we have mentioned earlier. Okay, so we'll get this double integral transformed into the polar coordinate system. So this is nothing but 4 times integral 0 to infinity integral theta is equal to 0 to pi by 2, and simplifying this, r raised to 2m minus 1 plus 2n minus 1 and plus 1. There are 3 places where you can see r here, r raised to 2m minus 1, here r raised to 2n minus 1, and this is one more r. That we can combine and write like this. Okay, and this into e raised to minus r square, I am writing like this, then cos raised to 2m minus 1 theta sine raised to 2n minus 1 theta, and then dr d theta. Okay, again you note that the two variables r and theta are independent of each other, and these limits of integration in the polar coordinates are also constants, so we can separate this. I can consider the terms containing r this, and terms containing say theta, second variable theta, and write this double integral as the product of two single integrals. So this is equal to 4 times integral r is equal to 0 to infinity. Okay, and what is the value of r raised to this power? This is minus 1 plus 1 will be cancelled, and you will get r raised to 2m plus 2n minus 1 into e raised to minus r square into dr into integral theta is equal to 0 to pi by 2, say cos raised to 2m minus 1 theta into sin raised to 2n minus 1 theta d theta. Okay, further I can rewrite these two integrals in the standard form so that we'll get some known expressions. So this is, I can write as r is equal to 0 to infinity r raised to 2 into m plus n minus 1 and e raised to minus r square dr, that is first part, okay, into I can write the second integral, this one, taking the other 2 here, 4 is 2 into 2, so 1 2 is written here, the second 2 is, I will write here, theta equal to 0 to pi by 2 cos raised to 2m minus 1 theta sin raised to 2n minus 1 theta d theta. Okay, so this is nothing but it is our gamma function with the value of that argument is m plus n. So this thing is gamma of m plus n, and this thing is nothing but beta of m comma n, if you see the definitions of gamma and beta functions. What was our left hand side? The left hand side was gamma m into gamma n. So we have proved that gamma m into gamma n is equal to this thing. So this implies gamma m into gamma n is equal to gamma of m plus n into beta of m comma n, which gives the required result beta mn is equal to gamma m into gamma n upon gamma of m plus n. So it is a very, very important relation between beta and gamma function. Okay, it's the relation between beta and gamma function. Okay. Here in this relation, m and n are any positive real numbers. As a corollary to this result, I can write down as a corollary, if m and n are natural numbers, then this beta m comma n, beta of m comma n, we can write as m minus 1 factorial n minus 1 factorial upon m plus n minus 1 factorial, which is obvious because we know that if m is a natural number, then value of gamma m is m minus 1 factorial and so on. So it follows from that very basic result. Okay, so nothing to prove actually. But these formulas are very useful in computing the value of beta functions. Let me write another a corollary from this result, which is very, very important, and that is what I'm going to prove is the value of, prove that the value of gamma of 1 by 2 is equal to square root of pi. So this is very, very important. This I can prove as follows. I will start with our definition of or the one result of beta function. So we know that integral 0 to pi by 2 say sin raised to p theta into cos raised to q theta. If you remember this is equal to 1 by 2 times beta of p plus 1 by 2 into q plus 1 by 2. Okay. Here p and q are any non-negative real numbers for every p and q greater than or equal to 0. Putting p and q 0, let us see what happens. Taking p is equal to 0 and q is equal to 0, we get the left hand side integral 0 to pi by 2 sin raised to 0 is 1, cos raised to 0 is 1 into d theta, and the right hand side is 1 by 2 times beta of p is 0 and q is 0, so beta 1 by 2 comma 1 by 2. So simplifying this, I will get integral of 1 is theta 0 to pi by 2 here. This in the right hand side, what I want to do is I want to apply that relation between beta and gamma functions. So beta mn is equal to gamma m into gamma n upon gamma of m plus n. So I'm using the main theorem what we have proved just now. So because beta mn is equal to gamma m gamma n upon gamma m plus n. So we are using this result. Okay, and the value of the left hand side integral is pi by 2. Here right hand side we get gamma 1 by 2 square. It's a real number which we don't know, and the denominator is gamma of 1. And we have already obtained the value of gamma 1, which is 1. So this gives me gamma of 1 by 2 square. This gives me gamma 1 by 2 square is equal to, I think I forgot something. Yes, there is a 1 by 2 here. Yes, this 1 by 2 is here. So that will be cancelled with this 2. And I will get gamma 1 by 2 square is equal to pi. Because value of gamma 1 is 1. Okay. And that gives the required result. So this implies gamma of 1 by 2 is equal to square root of pi. So very important value in mathematics, gamma 1 by 2, very useful. And one simple small example based on this beta gamma function, how to find the value of the beta function at some point. So let us find value of beta 5 comma 3. So evaluate beta 5 comma 3. So what we are going to do here is, I will write beta 5 comma 3 as say gamma 5 gamma 3 upon gamma 5 plus 3 using the relation between beta and gamma function. This 5, 3, everything is integer here. So I can add gamma 5 as 1 less than that, 4 factorial, and gamma 3 is 2 factorial, and this gamma 8 is 7 factorial. Okay, because gamma n is n minus 1 factorial. So I'm using this result. And this you can simplify. You get 1 into 2 into 3 into 4 into 1 into 2 upon 7 factorial. That is 1, 2, 3, 4, 5, 6, 7 multiplication. So 1 to 4 will be cancelled here. This will go with this. And here, this is 2, 3 is 6. So what we will get is 15 sevens are yes or no, yes, 1, 2, okay, so nothing is left. So yes, 15 sevens are 105. So we get 1 upon 105. Is it right? Yes, 1, 2, 3, 4, 2. Yes, yes, okay. So this is the value of beta 5 comma 3. So this is about relation between beta and gamma function and some consequences of this main result. In the next lecture, we are going to prove an important theorem about gamma function, which is known as duplication formula. Till then, goodbye.